Welcome to another in the series of Salford Systems online training videos. This is Dan Steinberg. Today we're going to be talking about cross-validation, and a little different than some of our other videos, we will have less in the way of live use of the software as we're trying to explain some concepts here. Cross-validation can be a very technical topic. We are going to treat it in this first session as a non-technical topic and try to give you the principal ideas. You should master at least as much as what we're trying to convey here, and it is optional if you want to go further. Okay, so let's get started. Cross-validation is a built-in automatic method of self-testing a model for reliability. It gives us an honest assessment of the performance characteristics of a model. It's trying to tell us, will the model perform as expected on previously unseen, that is, new data, which is what models are usually designed to make forecasts for. Cross-validation is available for all principal Salford data mining engines, and this all started with the first of our data mining engines, namely CART. The CART monograph, which was published in 1984, was decisive in introducing cross-validation into data mining, and it has spread throughout the current practice, and it's now a dominant methodology. Many important details relevant to decision trees and sequences of models were developed in that original monograph for the first time. That monograph is a landmark for many reasons, and one of the reasons is its treatment of cross-validation. Although it's a difficult book, we do recommend that our readers and our users get a copy and refer to it from time to time to see if they can gather some useful insights from the book. Cross-validation is a testing method, not a model development method. But why go through the special trouble to construct a sophisticated testing method when we can just hold back some test data? Well, when working with plentiful data, it makes perfect sense to reserve a good portion for testing. We work with quite a few large clients, both as software providers and as consultants, and it is not unusual to hear of people building credit risk models with 150,000 or more training records and having 100,000 or more records for testing. Similarly, in the direct marketing world, there are people working with 300,000 and more records for training and using 50,000 and more records for testing. In those circumstances, if one of your models performs as well or better than expected on a test sample of that size, most people will feel pretty confident in the results. However, not all analytical projects have access to large volumes of data. So the principal reason, but not the only reason, for cross-validation is data scarcity. When relevant data is scarce, we face a data allocation dilemma. If we reserve sufficient data to conduct a reliable test, we find ourselves lacking training data. If we insist on having enough training data to build a good model, we will have little or nothing left for testing. In this little diagram below, you can see there's an orange and a blue part, and you can imagine that we have a little slider, and we can make the division into train and test however we like. This is on a percentage basis. A common division of data is 80% train and 20% test. So suppose you had a really small data set with, say, 300 data records in total. If you use the 80-20 split, you'd have 240 to train and 60 to test. So we have a tough decision here, which is how much data to allocate to test. And I'm showing that slider being set to different positions at different locations here. You can see that in the top panel, we are favoring the testing part of our work, but we're making it very difficult for us to learn a good model in the first place because we've reserved so little data for training. At the bottom, we've done just the opposite. We've made sure that we have adequate data for training, but we've left so little for test, it'll be hard for us to put much faith in the results of the test. Now, how do we measure the size of a data set? Well, in most of our real-world applications, we see unbalanced target data. In most classification studies, the target or dependent variable is distributed in a very unbalanced fashion. We usually have one large data segment, the non-event, which is actually the event that we're not terribly interested in, and a smaller data segment, which is the event, which is the subject of the analysis. For example, who purchases on an e-commerce website? Who clicks on a banner ad? Who benefits from a given medical treatment? What conditions lead to a manufacturing flaw? When the data is substantially unbalanced, the sample size problem is magnified dramatically. So you have to think of your sample size as being equal to the size of the smaller class. If you only have 100 clicks, it is useful to think of your problem as being limited to a data set of that size. It does not matter much that you also have 1 million non-clicks. The strategy of cross-validation is sample reuse. Any one train test partition of the data that leaves enough data for training will yield weak test results because it's based on just a fragment of the available data. But what if we were to repeat this process many times using different test partitions? Imagine the following. We divide the data into many 90-10 train test partitions and repeat the modeling and testing. Suppose that in every trial we get at least 75% of the test data events classified correctly. This would increase our confidence dramatically in the reliability of the model performance because we have multiple tests which are at least slightly different. So, some technical details. Cross-validation requires a specialized preparation of the data, somewhat different than our example of repeated random train test partitioning. We start by dividing the data into K partitions. In the original CART monograph, Breitman, Freeman, Ocean, and Stone set K equal to 10. K equal to 10 has become an industry standard both due to Breitman and also other studies that followed, and we mention an important one at the end of this set of slides. These can't be simple random divisions of the data into 10 parts. The K partitions should all have the same distribution of the target variable. So in this case, that means the same fraction of events, and if possible, we want the sizes of the partitions to be as equal as possible as well. And we have a little bit more to say about that later in case you were interested enough to try to create your own cross-validation bins or partitions. But it does take care to get it right. The important point for the typical user is that all of this is done automatically for you in SPM software. The Salford Systems tools will generate the proper cross-validation partitions for you. And these slides here, this video is intended just to give you an idea of what's going on behind the scenes. But the more ambitious students can, of course, go on to try to do some of this in a manual way to get a better understanding of what this is really all about. So we have over here a display which shows the data having been divided into these 10 parts in the right way. And what we see is that we have highlighted different numbers depending on the row that we're looking at here. So now we'll explain what that is all about. Once we've divided the data into our 10 parts, we're now going to build an equal number of models. So if the data has been partitioned into 10 parts, we're going to build 10 models. Each model is constructed by reserving one part for test and the remaining parts for training. In this case, there'll be 9 parts for training, 1 part for test. If k equals 5, then each model will be based on an 80-20 split of the data. If k equals 10, then each model will be built based on approximately a 90-10. Don't forget that when you do cross-validation, these numbers don't turn out to be exactly equal and exactly as we're talking about it here, because in order to get the target variable distribution right, you might have to make the bins a little bit uneven. There is nothing wrong with considering k equals 15 or k equals 20, but it can be a mistake to use too many. In this strategy, it is important to observe that each of the k blocks of data is used as a test sample exactly once. Let's look back at one slide and now recall what it is that we've just been talking about. In the first row, block number 1 has now been highlighted, meaning it's been singled out for test. So the training or the learning is done on the remaining parts. We go through the whole process of building and testing a model, even though the testing is not going to be particularly persuasive because it's based on a small fraction of the data. We set all that data, all those results aside for later review. We now go on to the second row. In the second row, we set a different portion of the data for testing. Notice that there is no overlap between block 1 and block 2. There is no overlap between the test portions. However, there is considerable overlap of the training portions. In the first row, we have partitions 2, 3, 4, etc., all the way to 10 in the training partition. In the second row, we have partitions 3, 4, 5, etc., through 10, plus 1 in the training partition, and only partition 2 is in the test part. And we march through each of these blocks of data until we finally get to the last row, in which block 10 has been set aside as the test part, and partitions 1 through 9 have been used for training. So what do we have now? We now have 10 models. In addition, we're going to build an 11th model, and the 11th model doesn't have any test data at all. It builds a model using training data alone, and because we have no test data, we have no way of immediately evaluating that main model. Running a little example now using the gb2000_cvbin.xls data, which is data that is made available to you on our website, and running our SPM version 6.8. We're going to use this little risk data set, 2,000 records. We're just going to set this up in the way we always have. Going to allow for all the variables as predictors, except this data set is a little bit different than the others, and there's 3 variables. There's a row ID, there's a uniform random number, and there is something called bin. We're going to take those out. We're not going to use them in this particular portion of the video. Now let's go to testing. Notice that the default is v-fold cross-validation, which is 10. You can change that to any number you like. So let's go ahead and run this. And the testing has been done automatically. Because the testing has been done via cross-validation, we don't actually see any test results on the main model display, but we do see test results in reports like the prediction success table and in the gains and ROC chart, where we can get the test results for the model that we have chosen over here. There is a different set of test results for every size tree. So if we go to this size tree, for example, and go to summary reports, we will get a different set of test results for the confusion matrix. And again, we will see a different report for the ROC curve and for the test ROC results. So how do we get those results? Well, here I'm showing you some of the breakdown on actually a different data set, but the concepts are exactly the same. We have a table which you will not get reported by the software. We use a special technique to generate these results. But what we have here are 2 classes, 0 and 1, and in every cycle of the cross-validation, you can see numbers 1, 2, 3, etc., all the way down to 10. You can see that there are some class 0s in the training data, and there are some class 1s in the training data, and there will be class 0s in the test data and class 1s in the test data for every one of these CV cycles. If you add up these two numbers, 634 and 113, you get 747, and you will see that when you go to the next row, 633 and 114, or 634 and 113, we're always ending up with the exact same number of records in the training data, and we're also ending up with the exact same number of records in the test data. It's always going to be either 70 and 13 or 71 and 12. It doesn't have to be that way, but we're trying to work it out that way. So this is an example of how the data might be divided up into the tenfolds. So what do we do with these 10 different models when we try to put all the results together in order to get our final results? So you have to think about things this way. For a specific size tree, and let's just think first about the two-node tree, we can generate a confusion matrix for each of the 10 cross-validation models. Each of those confusion matrices will be based on approximately 1/10 of the data, the 10th that has been held back for testing. What we're going to do is we're going to cumulate, that is, we're going to add up those confusion matrices until we end up with one aggregate total confusion matrix. That is the confusion matrix that we are going to assign to and attribute to the main model, that is the model that was based on all the data. Then we're going to do it again for different size trees. And that's how we're going to end up constructing the curve that we see in the SPM software. So this curve over here, which is displaying a normalized version of the error rate, and therefore the misclassifications, this curve is derived from the summation of those confusion matrices from the 10 models that we're not actually showing here. They've been run behind the scenes. So interestingly enough, this curve here is indirectly derived, and we are assigning it to the tree that has been built on all the data. If you ask whether that could be a legitimate methodology, the answer is yes. If you ask whether it yields reliable results, the answer is yes. It may seem a little bit surprising because the methodology is indirect, but it is spectacularly reliable and successful. I have a slide here just for the advanced users. This slide over here explains how we align the results from the main tree with each of the CV trees. And this alignment is done via something called cost complexity pruning, and this will be discussed in a later, more technical video. So, we've already talked about the summing of the confusion matrices, and I just want to point out again that because we're summing correct and incorrect counts, and we're summing across all 10 test partitions, and the 10 test partitions together are equal in size to the original training data set, we end up with a hypothetical test set that is actually equal to the size of the original training data. So, here are some important points. Cross-validation is not a method for building a model. It is a method for indirectly testing a model that on its own has no test performance results. In classic cross-validation, we throw away the K models built on the parts of the data. We keep only the test results. Modern options for using these K different models exist, and you can save the K models in SPM software if you want. What can you do with these different models? Well, you could use them in a committee or an ensemble of models, a modern methodology in which averaging the predictions of different models is often better than using any one model. It might also turn out that one of the CV models might be more interesting than the main model. But this is a rather advanced topic and is not commonly used. probably be used only in a situation where you have the time and you are willing to examine in very, very close detail every little detail of the tree that you're finally going to publish and use. Reviewing again the topic of does cross-validation really work? We have done our own testing of cross-validation by starting with huge data sets and then extracting a small training data portion and pretending that was all the data that we had. We then used the cross-validation methodology to obtain a simulated test performance, but then we ran what would be a conventional test, making use of some of that large volume of data that we had available. What we found was that the error rate that was being predicted by cross-validation was usually very close to the error rate that we got when we actually had some real test data to run a conventional test set test on that same model. These tests convinced us that cross-validation is reliable. The CART monograph also discusses similar experiments conducted by Bryman, Friedman, Ocean, and Stone. They come to the same conclusion while observing that 5-fold cross-validation tends to understate model performance and that 20-fold may be slightly more accurate than 10-fold. So, how many folds should you actually use? We already said that the industry standard is 10, but not many people understand why, and not many people understand that you actually have some choices. Well, think about 2-fold cross-validation first. You divide the data into 2 parts. You first train on part 1 and you test on part 2, then you reverse the roles, and then you finally assemble results. The problem with 2-fold cross-validation is that when we train for the purpose of testing, we're only using half the available data. So the models that actually get tested, the cross-validation models, are nowhere near as good as models that would be built on much larger fractions of the data. So this is a severe disadvantage to the learning process, and what it usually means, 2-fold cross-validation in similar smaller numbers, 3, 4, 5, they tend to be pessimistic. That is, they tend to suggest that your model is not as good as it really is. So the spirit of cross-validation is actually to use as much training data as possible. So Bryman, Friedman, Ocean, and Stone actually find that 20-fold is better, meaning gives you more precise estimates of the actual performance of your model than 10-fold, but only a little bit more. And at that point in time, which is writing in the early 1980s, they felt that 10-fold was good enough given the speed of available computers. Today, if you're working with similar sized data sets, we are working with computers that could be as much as 1,000 times faster than the computers of that day, perhaps more. And so the idea of a painful wait for those small data sets just doesn't exist anymore. In other words, we don't see any reason why you might not lean to going to numbers that are a little bit higher than 10. If you go too high, for example, if you try the so-called leave one out methodology, which is setting the number of folds equal to the number of training records, this is an extremely bad idea. It does not work well for trees, and we don't have time to explain why that's so in this video, but we simply advise you not to use those very large numbers when you're talking about classification trees. The results that we reported from Bryman et al. Were essentially reconfirmed with the exact same conclusions in a paper written by Ronnie Kohavi in 1995. It's called A Study of Cross-Validation and Bootstrap for Accuracy Estimation and Model Selection. He also comes down on the side of 10-fold and also observes that results could be a little bit better for the 20-fold. So, suppose you want to create your own folds. We want to remind you again that this needs to be done with great care with smaller samples. take an example. Suppose you have 100 records divided as 92 records are zeros and 8 records are 1. Well, the first thing to observe is that you cannot have tenfold cross-validation here because every fold must have at least one example of an event, and you've only got 8 of them. So the maximum that you can push cross-validation to is 8-fold. So let's try for 8 folds then. If we try to make 8 folds, then we're not going to be able to have every fold have exactly the same number of zeros and ones. So our recommendation here would be you would have 4 parts with 11 records of y equals 0, and of course you're going to have 1 of the y equals 1s, and then you're going to have 4 parts with 12 records, and the remaining record in each one of those parts is going to have a single y equals 1. What happens there is that you get the response rate, which is the same as the distribution of the y variable, as similar as possible. And this particular division is much better than the one above, where we have 7 parts with 11 zeros in each part and 1 part with 15 records, because you're going to have a situation where you have quite a big difference in the distribution. My slide over here says y equals 1, and it should really say y equals 0. Okay, so points to remember. The main model in CV is always built on all the training data. Nothing is held back for testing, and that means that when we have built that model alone with no supporting other models, we have no idea what the test performance of that model is going to be. Let's look at a data set that has 100 records divided as 92 zeros and 8 ones. The first thing to observe is that it is impossible to do tenfold cross-validation here. Why? Because each fold must have at least one example of the target equal to 1. We've only got 8 of them, so the most that we can do is 8-fold cross-validation. So there are a few different ways in which we could construct that. One of the ways in which we could do things is we could have 8 folds. 7 of them would have 11 of the zeros, and each of those 7 would also have 1 of the ones. And then the last part would have the remainder, which would be 15 zeros and the final 1. But that's not such a good idea, because the response rate in the different bins are, well, they're all the same for the 7 parts, but they're quite a bit different for that last 8th part, relatively speaking. That's 1 and 15, 1 to 15 versus 1 to 11. It is better to divide the data in order to get each of the bins as similar to all the others in the response rate. If we divide with 4 of the partitions with 11 zeros and 4 of the partitions with 12 zeros, things are going to be more similar to each other across the bins, which are going to give us less variation due to the construction of the bins. This is a topic which, of course, we can't go into in further detail here. We just need to point out that this is something that you will have to pay attention to when things don't naturally divide perfectly according to the number of folds that you want to run. So, points to remember. The main model in CV is always built on all the training data. There is nothing held back for testing. When we build that model, which is before we build the CV models, we have no idea what the test performance of that main tree or that main model is going to be. Now, if you were to run CV in several different ways, for example, varying the number of folds, or varying the construction of CV folds by varying the random number seed, you would always get the exact same main model, because the main model is always built on all the data, and it's always built before we do any of this partitioning of the data into parts. But what will differ from one variation of cross-validation to another is the estimate of the test performance. So it's useful to know if the results are actually going to be sensitive to these parameters. If you run battery CV, you rerun the analysis with different numbers of folds. So as the number of folds gets larger, things should look stable. The battery CVR uses the same number of folds in each replication, but creates the K partitions based on different random number seeds. This is expected to yield reasonably stable results, but you never know. Unstable results suggest considerable uncertainty regarding your model, and if the results are sufficiently unstable, you might consider trying to find ways to revise and refine your model to see if you can get those results more stable. If you're going to try the batteries, let me just point out where you can find them. They're located on the Model Setup dialog, and there is a battery tab for most modeling methods. And over here, you can scroll down. Here is CV. If we add this, let's have a look and see. It's going to automatically build 5, 10, 20, and 50-fold cross-validation results. If you try CVR instead, then you're going to get a replication of the whole process of dividing the data into your partitions and then running the models. But each time you do the preparation of the data, you're going to start with a different random number seed, which means that the records that end up in each of the folds could be slightly different, and this will make a difference. In terms of CVR repeat, I don't recommend going as high as 200 normally. A number like 30 would be a perfectly reasonable number to get an idea of how stable your cross-validation results really are. Okay, that brings us to the conclusion of this particular video. We hope that you have found it useful, and we look forward to meeting with you again on another topic.